All right, so as we look at bases other than E, one of the main applications, we already talked a little about half-life in a previous lesson, but one of the main ones is this idea of compound interest. For a deposit of $1,000 at 8% interest compounded n times a year, okay, if we're compounding it once a year, we have our compound interest formula, all right, and this formula is a little bit off. It's missing one thing here, and that is the t got cut off. It's n times t, okay? Now, technically speaking, we're only dealing with 1 year, so t would equal 1, okay? So that's why we can just go ahead and leave it here as to the n, because t equals 1 year in all of these, okay? Now, when we're dealing with this, our amount at a given time is going to be that p. P stands for
Initial.
the initial amount, okay, and in finance terms it's called our principal with a PAL at the end. That's the amount that we're either borrowing or we're investing. So our principal in this case is 1,000. And then we have 1 plus. And remember I told you when we were looking at half-life, really what this boils down to is a unit conversion. We make 8% a year, but how much do we make per compounding period? Okay? So 0.08 divided by the number of times we compound. So if we're compounding once a year, then that's the rate that we're dealing with. If we're compounding twice a year, then our unit of time is really 6-month periods, okay, that happen twice a year. So we wouldn't be making 8% each of those periods, we'd only make 4% each of those periods. If we were compounding quarterly, 4 times a year, then we would be making 2% every quarter, okay? So that's what we're dealing with here, and that's why we divide that 0.08 by the n, okay? And then likewise, instead of t being 1 year, we now need to convert that exponent into the number of compounding periods we're dealing with. Again, it's a unit conversion problem, okay? So, looking at our table over here, if we're just doing this once, compounding 1 time a year, then we just have 1,000 times a 1.08, which would be $1,080. Okay? If we're compounding it twice a year, then we need to plug in n equals 2. Alright, so for n equals 2, we have 1,000 times a 1.04 squared. Okay? And how much would that give us? $1,081? And 60 cents? Okay? If we were to do it 4 times in a year, here we have quarterly that we were talking about. We're making 2% every quarter, and there are 4 quarters in a year, so we have to compound it that many times. And how much does that make? 1,000. Not quite. 1,082.43. Okay, it should be going up. The more we compound, the more we make. So it should be going up. Okay, and then for 12, we have 1,000, and it's 0.08 divided by 12. Okay, so that's 2/3%. So it'd be 0.00666 and so on. to the 12th power.
1082. Oh wait, will you wrap this
What do we have? Come on, you guys are the ones with the calculators. Got these fancy calculators. You don't want to use them.
1082.99.
0.999?
Yeah.
Okay, so if that'll be 83.00, right? Okay. And then if we do 365, so here we're compounding daily. Okay. So 1,000 times 1 plus whatever 0.08 divided by 365 is, to the 365th power.
1083.
Okay? So you'll notice each time we compound more, it goes up a little bit. Now after 1 year, the difference really isn't much. Okay, difference of 328 from our 1 to 365. Okay? However, as time goes on, that adds up and adds up and adds up. So that's a good little reminder for us of how that worked. But let's think about this kind of structure here. This 1 plus r over n to the n power. Okay? If I were to multiply this 1 plus r over n to the n, if I were to multiply this by an n over n, I would have n plus r over n to the n power. Now I want you to think about this. If I kept making n bigger and bigger and bigger and bigger and bigger, okay, then the rate would kind of make less and less of a difference, right? Okay? Because that r, whatever it was, at most it's a 1, makes less and less of a difference there. Okay? And that's what we kind of see here as we look down below, and you can see here where the number e comes from. If we took that 1 plus 1 over x to the x power, or you could rewrite it as x plus 1 over x to the x power. If we kept making x get larger and larger and larger, you can see here we end up with 2.71828 and so on, which happens to be what e. It's approaching the value of e. Okay? So this is where this number e comes from. And you can kind of see here, we can develop this from our formula for compound interest. If I took the limit as n approaches infinity of my compound interest formula, p is a constant, so I could pull that out. Alright, and then notice what's inside there. I have a 1 over n over r, and I could rewrite n as n over r times r, right? I'm rewriting this as this, and I rewrite r over n as 1 over n over r, and notice that now fits my formula. Okay? Now, if I replace n over r with an x, I can take the limit of just that and then raise it to the power. That's one of our rules for limits. If we have a power inside the limit, we can just take the limit and then raise that to the power. Okay? Well, you'll notice here, this is e. So it's p e to the r. That's where the perk comes from. If t wasn't 1 year, this all would still apply. We just have a t floating in there all the way down. Okay? So, gives you a little bit of an insight into where some of this comes from, and again, we're dealing with these exponentials with different bases, and that e to the x, obviously we have the derivative of, but then if we have other levels of compounding, then we'll have other bases, okay? So think with this in light of this e to the r, how often is that compounding? Continuously, okay? Or every moment, or an infinite number of times every year you could think of, okay? That's the idea of that, and that's why that's our continuously compounding interest. Mm-hmm.
So could you use per for half-life as well, or no?
No, because there, the compounding nature is in relation to half-lives. And that's a fixed amount. It would be like as the half-life approaches infinity, you get this. But yeah, there you have a fixed amount that you have to stick with. So.
Mr. Nixon?
All right, so let's try a quick example of this. This is kind of a flashback to some of your algebra classes in the past. So try to use the formula that we had looked at to find this quarterly, monthly, and continuously. And you guys can you can work with a friend as well on this, okay? Yeah, notice this one does have 5 years, not just 1 year. Okay, so we do need to incorporate the t. Okay, so the amount is p times 1 plus r over n to the n times t. Or if it's continuously, you have p times e to the rt. All right, so which of these should be the biggest? The continuously. Which one should be the smallest?
Quarterly.
The quarterly, okay. So if you set up your formulas here, it should look like this. Okay, the quarterly, you're dividing the 0.05 by 4 in the parentheses, you're multiplying 5 by 4 in the exponent. For the monthly one, you're dividing the 0.05 by 12 on the inside, you're multiplying the 5 years by 12. Again, remember it's just a unit conversion. This is a quarterly rate and 20 quarters. Okay? This is a monthly rate of interest for 60 months. Okay, over 5 years. And then over here we have the continuously, p times e to the rt. Alright, so let's get some answers here. What did you get for the quarterly one?
3,205 and 9 cents.
Okay. And how about for the monthly?
3,208 and 40 cents.
Okay. And how about continuously?
3,210 and 6 cents.
Okay. So in 5 years it made a difference of almost $5. Compounding quarterly versus compounding continuously. Okay. I will tell you most financial applications use compounding monthly. Like when you do, if you have a credit card and you don't pay your balance, you're going to end up paying interest and that will compound monthly. If you have a car loan or a mortgage, typically those will compound monthly. Okay? Questions about this? All right. So then we have this kind of an idea, all right? We've got this bacterial culture growth. This is kind of a different model here, okay? The concept, though, is similar. Now, this model you may recognize from pre-cal honors, you saw it just briefly. This is what's known as a logistic model. It's often used when there's a certain capacity that's possible. Okay, here we're growing a bacterial culture in a petri dish, and obviously that petri dish has a maximum amount of space that you can grow bacteria on. So at some point it's going to slow down and even stop potentially. But these functions look like this. Okay, and they can be used for modeling growth of bacteria. They can be used to model like an outbreak of a disease. You know, it starts kind of slow and then lots of people get sick really fast, and that's kind of when we start to notice it. And then fewer and fewer people are getting sick because everyone's already sick or they've already been sick. Or you can even model it for people showing up to a ball game. Okay? If you do use data, you come up with some kind of function, you could say, okay, you know, 3 hours before the game starts, we can just have a couple of gates open, you know, because not as many people are coming, but then here's the window of time where we got to have the most people working and all the gates wide open, and then we can start shutting them down when it gets this close to game time or this much past the start of the game because barely anyone's coming in at that point. You know, so these models can be used for lots of different stuff. But anyways, if we take a look here, we have this model y equals 1.25 over 1 plus 0.25 e to the negative 0.4 t, where t is greater than 0. This y is the weight of the culture in grams, t is the time in hours. So this says find the weight after 0 hours, 1 hour, and 10 hours, and then what's the limit as t approaches infinity. Okay? So let's think about this. If I have t equals 0 hours, what does that give me? 1. Okay? 1. Because, notice here, I have e to the 0 then. So it's 1 plus 0.25 times 1, or 1.25 over 1.25. So that just equals 1. So that's easy. 1 gram. Okay? Now you'll need your calculators for B and C. If we have 1 hour, what do we get? $1.07. Okay. Is that 0.7005? So let's do 1.071 just to do 3 decimals. Okay? And then how about for 10 hours? $1.244. Okay. So then think with me here. What's the limit as t approaches infinity? 1.25. Okay. How'd you come up with that?
Because if you look at just the e to the negative 0.4 t, the greatest that could ever be is like 0 as t gets greater and greater. So then it's just 0 times just 0.25, so just 1.25 over 1.
Okay. Yeah. That's 1.25 grams. That's going to be what it's approaching as t approaches infinity. Again, what Austin was saying here is that this part right here is what you really got to look at. E to the negative x, the 0.4 really doesn't matter. That just tells us how fast we're going to get there. But e to the negative x has a horizontal asymptote at 0. So this is going to approach 1 plus 0.25 times 0, or just 1 in the denominator. So 1.25 divided by 1 is that. Now, You know those models I was telling you about? That numerator is our capacity. So like if we were doing the ball game, you know, and our stadium could hold 50,000 people, then our model would have a 50,000 at the top. So your capacity goes at on the top there. Mm-hmm.
Would you not be able to use Boba bond for this?
No, because it's not a those aren't polynomials. So, okay. All right, so just a little bit of practice in that unit, not really any calculus here in this lesson, but just some good practice using some exponential growth models and things like that, okay?